All right, today we'll continue our discussion from where we stopped last time. Right. So the first thing I want to show you today is how uh, uh, digital redesign process is implemented. Okay. So here you have a uh, analog control system, right? Let's call it the plant here. You can see, and plant is controlled by an actuator, right? So always you have the controller, after the controller is actuator, right? So you have the plant and in front of that the actuator, right? Whenever you see control system, sometimes you don't see the actuator because it is included as part of the plant itself. Then you have the controller over here. Okay. So what you see here is actually pretty much the same thing we have been dealing with in the last semester, that is a continuous time control system. Okay. Uh, let me get rid of this. Now, you will feel very comfortable seeing this control system here, right? Because you have spent a lot of time on continuous time feedback um, loop, right? Like over here. Now, if you look at the modern way of controlling systems, it is not exactly this way, right? We want to use microprocessor based controllers, microcontrollers, single board computers, all discrete devices, right? To implement the controller function over here, CS. We do not implement CS very much these days, okay? So we want to bring in what is called CZ. That is a discrete time controller. But you can't abruptly replace CS with CZ because you need to look at all the nitty-gritties, compatibility, communication, right? Everything, especially the communication. How should the discrete time controller, right, should communicate on one hand with the inputs coming into the system, and also how should it communicate on the right hand side to the actuator, right? We have to clinically implement those two processes. Now, if you look at what's on the left hand side, discrete controllers cannot accept analog signals like over here. This RS, once you get YS over here, right? The difference is RS minus YS, and it is the error ES, continuous time signal. The discrete time controller cannot receive, right, continuous time signal. So therefore, you have to change RS into RZ, which means you have to discretize RS. Okay. If you have discretize RZ, which means the reference as a set of samples, I think you can understand it is easily doable. If you use a computer to plan a trajectory like RS, reference trajectory, right? You can sample it into a number of steps, right? Using a certain sampling interval. And you can store all these values of the reference signal as RZ over here. So therefore, that is not a big problem. Sampling a signal is not a big problem, okay? And you have to make sure that it is not just RZ. There's another signal coming, that is a feedback, right? From the right-hand side over here. So it also has to be a discrete signal, okay, with the same sampling interval. So you have to discretize the response also ys. Okay, so let's say you have it, and the two signals, the reference signal as well as the response signal, right, are now available in their discrete format, okay. In that case, what you want to do is, at a certain time stamp, right, let's say now, you read the reference value, you read the response value. These are two samples, right? You get the difference between the two, and that is your error. That is given to the discrete time controller. Okay. Once you do that, the discrete time controller produces a discrete signal, which means a number, right? And after another time interval, sampling interval, it produces another one. Okay, it goes like that. So one sample at a time. Let's say it is 1 second sampling interval. So every 1 second, it produces its output over here, right? And after that, let's say the controller takes 1 millisecond to produce that output. And then from that point onwards, 999 milliseconds, nothing happens, right? Nothing happens. It is just idling. It doesn't look at the plant. What's happening to the plant is not of any concern, right? And after 1 second, after 999 milliseconds, it wakes up. And then by that time, R is it uses steps up into the next sample, and Y is it is also having its next sample. So it's a next timestamp after 1 second. And there's a new error here, right? And controller operates its loop again and produces another signal. That is the control signal, discrete time, right, after the previous one. So again, after that, it goes to sleep 999 milliseconds. So this is how it operates. Okay, right now, but if you look at bulk of the objects on the right hand side from this point onwards, right, analog actuator is analog actuator, plant is analog, and so on. So this discrete signal, all right, cannot be communicated directly to the actuator. So therefore, you have to convert the discrete signal into a continuous signal, and you use digital to analog converter here. Digital to analog converter here. So it will create an analog signal which goes to the actuator. So actuator is happy. Now you have the analog signal, which means you have the signal at all times, not only for 1 millisecond, but for the entire 999 milliseconds, you have the same signal. It keeps it, latches it, right? Not so early it was just like this. 1 millisecond, there's a sample, and after there's nothing. It was like that, okay? But now, because of the digital to analog converter, the value is kept like that for 999 milliseconds, right? Until it changes by, it is changed by the controller again, right? In the next cycle. So then actuator actuates according to that analog signal. The plant will undergo certain changes. Therefore, the response changes. The new response is measured by the sensor, which is, say, analog sensor. The analog sensor output cannot be fed back over here because this is discrete signal, right? Therefore, you have to convert the sensor response to a discrete format using analog to digital converter. Okay, so it converts analog signals to discrete version using same sampling interval. And over here you have YZ, which is in time domain YK. So this is the simple thing, but extremely important that to understand this process, and we call it digital redesign. So you receive the continuous plant over here, right? You can start with the continuous plant, even though you know you are going to eventually develop a discrete time plant, right? You use all of the techniques that you learn in semester 1 and design the controller, because Digital control is basically conversion from their analog counterparts. Okay. All right. Any questions, please? Okay. So these two components are extremely important. DAC, which is digital to analog converter, and ADC, analog to digital converter. Right. The next slide, we're going to look at the two components. So let's take the DAC first, digital to analog converter. So you might be interested in knowing what this block is and what are the internal components and the mathematics, right, that explain the function of DAC. So digital to analog converter is basically converting the digital signal to analog version. Okay. So it's like you have set of samples like that, right? Like that. And you want to draw a line connecting these samples. And of course, you can understand there are so many ways to do that. Okay. If you are given set of samples, and if I ask you, okay, what is the best fit for all of these samples, right? You can do various things. Okay. Smooth curve or flat top or ramp, right? A lot of mathematics on signal reconstruction, okay, using set of samples. So let's look at some of the very basic things and mostly or frequently used techniques, right? Now, I've taken a little piece of the control system over here, right? Digital to analog converter, so over here. And if I expand this, I can show it like this to you, right? You have the digital controller, which produces FK, let's say FK, right? Or better, I should have used UK over here because it's the control signal, right? And it's a discrete, okay, discrete version. And you got to have some sort of mathematics over here, right, which will produce FT or UT, right, continuous signal. This is exactly what we want. We want to have a continuous signal, right, to be fed to the analog actuator. So different people have come up with different techniques, different algorithms, right, for this plot, which take samples and reconstruct, right, some sort of continuous signal. Now, if you go to the basic math, right, Taylor series is what comes to everybody's mind. Okay, if I give you a set of samples and ask you, get me a best fit, right? What is the best curve that satisfy all of these samples, right? You can start off with the Taylor series. Taylor series says, okay, you have FKT, right? At any moment of time, you have the sample, the kth sample, right? And at that point, you need to know the gradient, right? Whether it is like this or that, whatever it is, right? Gradient. So to calculate the gradient, you need to know one before that or one after that, depending on which one you use, okay? Whether it's forward difference or backward difference, right? Or sometimes you need both of them. What was before that and what is after that. And then you can do some sort of bilinear approximation or Tastin approximation. So if you're interested in, you can read all of these things, okay? So you need to have some reference of the neighborhood, the sample before the kth sample or after kth sample, right? Whichever you want to use, then you can get the gradient, right? Gradient. So if you know the gradient, right, you can calculate by a little time, right? And then get to the value in the neighborhood, right? So you need to do all of these things before you get to the next timestamp, because at the next timestamp, right, the sample is available. The sample becomes available at the next interval. right? If you do not know the next sample, right, you can look at what was it before that. I look back and figure out approximately the gradient, and you go along the gradient because that's the only um, possible assumption at this moment, right? When nothing is available, right? You have the previous sample and you have the sample at present, and then figure out the gradient. Then you use this time t minus kt, right? T is your time after k, right? Little time after k, t minus kt, and you multiply that time with the gradient, right? You get the additional height, and you add that to uh, the sample at k. Okay, and somebody says it's not accurate to get only the gradient, right? Because it can be a curvature, right? Can have the second derivative, the acceleration, right? Or even before that, after that, you have jerk or snap and all these things, high order derivative, right? So you can keep writing these numbers if you want. If you want to have very precise signal generation using the samples, right? This would be a bit higher order reconstruction equation. So this is what is uh, being implemented inside the sample and data reconstruction device. Okay. Now, let's say we don't want to make things unnecessarily complicated, right? And let's if we assume, okay, we want to get only the first one, zero the whole, you can do that. There are a lot of controllers, digital controllers, where the DAC or digital to analog converter is just a zero order whole circuit. It's only the FKT. In that case, you maintain the level, right, until you get the next sample. And once you get the next sample, maybe a bit higher, you maintain that level, right, like a staircase. That is not the best, but it works because most of the industry applications, right, you are just fine with that. And if you have samples very close to each other, right, you don't leave this error to continue for long, right, because you get the next sample pretty quickly. So that is how the industry works. That is how the industrial engineers would like to practice, right? Don't make this too much complicated with very complicated mathematics, right? Just stick to the first one, the first term. And if you do that, your digital to analog converter is simply a zero order Paul circuit. You don't have this one, or any other higher order terms. Okay? Any questions? So if you use, for example, the first order term also, then you are not actually maintaining the level at K, right? The control signal will look like this. So it changes from this sample to the next sample. Okay? So it doesn't keep the level constant. Right? So there you see the zero the whole circuit. Right? You can see the samples over here coming like that. This is UKT or FKT. Then you have the zero the whole circuit and then the analog version of that. Right? You can see the levels are maintained. Sample height is maintained for one sampling interval. Right? And when you get the next one, you maintain that one. It goes like staircase. Okay, the mathematically this is how we write it. Ft is equal to fkt, right, from kt to k plus 1t. Okay, the entire period, one sampling interval, the level is fixed, right, constant. Right. Now, this is how a typical digital control system look like, right? Can see the RK, the discrete signal, reference signal, and yk over here, right? The discrete response, and then the difference between rk and yk is the error, again discrete. It goes to the discrete controller. I think we looked at the discrete controller. Basic discrete controller is basically a difference equation. It keeps the present error and the past errors, and also past control signals that it has unleashed to the actuator side. And by combining all these things, right, it generates the present control signal, UK, which goes to the zeroed hole, produces UT, continuous signal, which goes to the actuator and plant together. So here GS is both plant and actuator together. And you generate the response, YT, continuous response. Use a sampler here. Here the sampler is analog to digital converter, simply sampler. Okay, there's no other thing, just a sampler which takes the samples of the analog signal at regular intervals and produces YK, right? So this is the entire discrete control system. Okay, see it over here, zeroed hold waveform. It holds the wave for one sampling interval like that. Goes. For sampler over here, if YT changes like this, right, a continuous waveform, you can see it over here. It takes the samples here, 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 like that. It generates the samples, right? I have written it like step case together with the zeroed hole. But in fact, if you don't have the zeroed hole, it's just the samples, right? Like this over here, right? I'll make this a little different in the text, okay? Without this zeroed hole effect, only the samples. Now, if you look at this control loop, how the control loop operates, right? In a discrete controller, you can write it down like this. Oh my God, this is 1, 2, 3, 1, 2, 3. So this should be 1, 2, 3, 4, 5, 6, okay? So sorry about that. The first thing is read YK and RK, right? You read RK and YK, right? This is a controller function, CZ. It has to do all these things, right? It has to read RK, it has to read YK as well. Then it calculates error, EK, is RK minus YK, right? Then it has to calculate the control signal, right? So you need to code your controller here, right? Whether it is a P controller, PI controller, PID controller, or any other controller, right? You have to break it down into a discrete format or differentiate